so I'm here, and so on and so forth, right? So this is now my computation graph, and here's the computation graph if I kind of show you the identities of the nodes, all right? But notice now that I have a bit more interesting pattern here that GNN could capture because it knows the color of the node. And assigning a color to the node of interest is inductive. In a sense, I can transfer the model to a new graph because there's always, whenever I embed, I know what node I'm trying to embed. Okay? So the point is this coloring is inductive. It is invariant to the node ordering or identities of the nodes. I can relabel the nodes, I can renumber them, but the structure, the shape of this computation graph and the pattern of white versus orange is going to stay the same, right? So here I have 1, 2, 3. Here I have 1, 2, 3. But the color pattern in the computation graph remains the same. That's it's kind of trivial, but it's important. Okay. So that's the first one, right? So I have now an inductive capability. How about does this increase my predictive power? And it does, right? Because if I take now the two graphs, the triangle and a square, and I do node classification, and I say, okay, what is now the computation graph for V1 versus V2? It will actually be different, right? Because this is for V1, we already worked it out, but for V2, it will be different, right? I'm going from V2 to neighbors. From neighbors, I go either back to V1 or I go to the next neighbor here. But from here on, I don't get to V2 again. So at this level, the pattern is different. So my GNN, if it accounts for the color as well, will be able to distinguish these two nodes. So basically, I'm in some sense able now to count the length of the cycle because I see when does the GNN kind of come back to where it started, right? And I see here it comes back in 3 steps, while here it will need 4 steps, right? At this level, I'm going to see only empty nodes, white nodes, and then here I'll start seeing orange nodes again. And if you use this kind of simple trick, then things start to work out very nicely. Here is for graph classification A and B. Even though computation graphs will have the same structure, the identity of the starting node is going to make this pattern be different from the other pattern. So I'll be able to distinguish node A from node B, right? And when I say why do I call this class of models identity aware? Because it's aware of the identity of the node that we want to embed, right? And this is my last example, which is about link prediction, and I'm trying to create an embedding for V1, and I want to try it for V2. And again, if I look at the computation graphs, they're going to differ at 2 levels, right? When I go from V1, I go to the neighbor, and neighbor of neighbor, and I can visit V0, while if I start at V2, I'm not able to visit V0 in 2 hops. So because these 2 computation graphs are different, these 2 nodes are going to be embedded in different positions, and I'll be able to say, link A occurs, but link B does not occur, or something like that, right? So that's the idea that I wanted to convey, kind of in an abstract way about this. Being able to differentiate between different nodes by using this simple, kind of very cute idea of labeling the starting node, the node of interest. Now what I want to do next is actually show you how to build a GNN using this type of node coloring, okay? That's what I want to show to you. So I want to now show you how to build a graph neural network, actually its architecture, and how to take account into these node colors when we are doing propagation. And the idea is that we are going to do heterogeneous message passing, right? Normally GNN applies the same message aggregation computation function to all the neighbors, to all the nodes, right? Right, in a sense that at the GNN layer, we apply the same message aggregation to each children or to each node below us. What we are going to do in a IDGNN is that we are going to do heterogeneous message passing. Heterogeneous in a sense that different types of message passing are applied to different nodes. So IDGNN will apply a different message aggregation function to nodes of different colors. And I only have nodes of, orange and white, but that's already good, right? So I'm going to apply a different aggregation or transformation here than I apply it to white nodes. So at a given layer, different message aggregations is going to apply based on the color of the node. So to be a bit more formal and precise, like H is our node embedding, and let's say that I first extract the k-hop computation graph. Here I'll label it with G raised to the power k, and then I'm given set the initial node features at layer 0, right? That's the input. And now the way my aggregation is going to go is the following, right? For now I'm going for all the nodes in the computation graph, and I'm aggregating I have a message function that is going to change depending whether the node of interest S is the starting node. Depending the node of interest V is equal to the center node, to the node of interest or not, and we are going to use different neural network functions to transform the embeddings, right? So the color gets considered here, right? The root node, the node of interest, gets a different color, so it gets to have a different message function. It means it gets to have different parameters. Right, so why does this heterogeneous message passing work? Suppose I have two nodes that have the same computational graph structure, but have different node colorings. Since we apply different neural network embedding computation, their embeddings are also going to be different, right? Here, I'm going to apply message function A to all of these nodes, while here I'm going to apply a different message function B to these nodes, so the messages are going to be different, and neural network will be able to capture that difference. Yes?
Is it possible that the loss function won't transfer any information such that the weights that are developed by neural net A and B are actually any different? Right, like is there a case where the node coloring wouldn't be useful, and so this heterogeneous message passing would just sort of like wash out?
Good question. So you are saying if I train this heterogeneous neural network, I initialize with some random parameters this guy, I initialize with some random parameters that guy. Why wouldn't just both neural networks converge to the same thing? And I think the answer is they might, but they won't if the identity information is important, because nodes have different labels even though they live on different cycles. So it depends on how the labels are. If the labels are such that the cycle length doesn't matter, then it's okay for it to converge to the same thing. But if we want to distinguish, then these things shouldn't converge, won't converge to the same thing. Yes?
So do we have a different message for each node in the graph?
Do we have a different message? No, I mean, what do you mean we have a different node?
Different neural net A, B, C.
No, we just have two. One is for white and one is for yellow. That's it. I have just two I have just two message functions. Message functions that I'm applying to these nodes and message functions that I'm applying to those nodes. Happy?
How many nodes can we add? Different.
I just have two colors, right? I only know who the root is, and everyone else looks the same to me. Yeah, it's just two. Yes.
Just connecting this GNN with the position-aware GNN, is one way of thinking about this GNN similar to if the node we're embedding is just the anchor node? Is that a way of thinking about what it means, the color?
Interesting. So you are saying is thinking of the color the same as thinking about the anchor? Not really, right? In the anchor, it's more like with the anchor, the intuition was where am I positioned? Am I, in the east or am I in the west? Here, you are more asked, how do I embed in my local network structure? And this is a more expressive way to capture the local network structure, right? So this is all about the locality. So it's very kind of microscopic or mesoscopic view, while the position aware was much more kind of macroscopically, where am I roughly situated in the graph? So these two are kind of orthogonal or complementary, and you could kind of apply both, right? Because they kind of solve orthogonal problems. Okay, good. Super. Anything else? Okay, so let's just to explain, so what's the difference between GNN and an IDGNN? The difference is here, right? In the GNN, the computation graphs will be identical. In the IDGNN, the computation graphs are structurally equivalent, but I can account through this heterogeneous message passing for the identity of the node, for having this special orange node. And this will give me more expressive power. So why does IDGNN kind of generally outperform GNN? Because IDGNN can count cycles originating from a given starting node, but the GNN cannot, right? And if this information turns out to be important, then this the IDGNN allows you to capture it, right? Right. So what you could also do, rather than having this heterogeneous message passing, you can actually, on this intuition of cycle lengths, you could actually create like a feature vector for nodes to actually count cycles, right? So we would have a fast version of this idea where you include identity information as an augmented node feature, and no need to do a heterogeneous message passing. And you could use cycle counts at each layer as an augmented node feature, and then use this with any GNN. Okay, so this would be, V1 appears in a cycle of length 0. This is length 1. This would be 2, 3, and so on, right? So that would be another way to kind of bring in similar intuition, but then not change the architecture. So let me summarize this part. So IDGNN is a general extension of the GNN framework, where we can apply the IDGNN to any message passing GNN, right? You could use a GCN convolutional layer, a GraphSage convolutional layer, a GIN convolutional layer, however you would like, right? And IDGNN will allow you to basically build more expressive graph neural network for both node, edge, and graph level tasks. The reason why IDGNN is more expressive is because it takes care of this identity node and allows you to basically have this special node and account for it in the message passing. So basically, now you have a graph neural network that is more expressive than the WL, so the Weisfeiler-Lehmann graph isomorphism test. And it's easy to implement, and actually PyG I know implements it, DGL I think also implements it, and so on. Yes, question?
What is the 1 WL versus like a 3 WL?
The 1 WL versus multiple WL is how dimensional colors are you using and how many hash functions are you using. Okay. So the bigger this number, the more expressive the test is. Okay, cool. So maybe what I want, or is there any more questions? No, yes.
Can we just think like this graph as a heterogeneous graph where like myself is like type 1 and then like all other nodes is type 2 and then we can run something like RGCN on that?
So you are saying, can I think of your graph as a heterogeneous graph that with two types of nodes, type 1 and type 2, and then run an RGCN on top of it? Yes, you can. Exactly. That's the sole point of all this. You could also use an RGCN that will be even a bit slower, but will achieve the same goal. Yeah. Okay. Cool. So good point. Great. Let me maybe finish the lecture today with kind of a bit more of a discussion and an introduction about how would you think of robustness of graph neural networks. The motivation is, right, how robust are graph neural networks, and especially how robust are they against adversarial attacks? And this line of research was actually motivated, especially by the research in computer vision, where basically you can take, you can ask a convolutional neural network, what is this? And it will say pandas. Now you add this type of noise to it, so you get this image, and here it will say it's a gibbon. Okay, and to me, this looks like that. Okay, so the point is that an adversary can come in, add just little kind of carefully decided noise or changes to the pixel values that are going completely throw off your classifier, and what looks like panda gets confused for a banana or some crazy thing. Okay, so these adversarial examples, the idea is that somebody carefully calculates this noise or this perturbation, and that small perturbation can really flip your classifier. And this was first discovered in 2015 for convolutional neural networks, right? So the adversarial examples are also sometimes reported in natural language processing, similar problems, as well as in audio, where again, small carefully crafted change can really throw off the classifier. And what this means is that the existence of these adversarial examples prevents, in some sense, reliable deploying of deep learning models, because an adversary can come in and get any classification result they want by just small manipulation, right? Adversaries may try to actively hack the deep learning model. The model performance can become much worse than what we expect. For this reason, deep learning models are often not robust, right? And this is a very active area of research to think about robustness and this what they call distribution shifts. So the question is, how would you generalize these notions to the graphs? And why is this important, right? Because the common applications of GNNs usually, are on public social network venues, or it's about, banking and transactions and so on. So there's a lot of monetary interests from search engines, social networks, recommender systems. And, adversaries have the incentive to manipulate the underlying model and try to hack the predictions of it, right? If you are in a search engine, you want to be ranked as high as possible. If you are in a recommender system, maybe and you are a seller, you want your product to be recommended to as many users as possible, so you get more sales. There's a lot of gaming happening all the time. So what I want to introduce to you is kind of a framework how to think about this for graph neural networks. So we want to study the robustness of GNNs. We are going to consider the following setting. The task will be semi-supervised node classification. So the graph is partially labeled, and we want to complete the labeling of the graph. And the model is we are going to use the simplest GCN to do this, okay? So the roadmap for the next 20 minutes is that we want to first describe several real-world attack possibilities. Then I will quickly show the GCN model that we are going to attack. So we know our opponent, that's important. And then I'll formalize the attack problem as an optimization problem, and then I'll show you some empirical results. Okay, so that's the idea. So if you are attacking a graph, what can you attack? You can either attack, we have the target node. This is the node for which the model will be making a prediction. And we are going to call this node a target node. And then we are going to talk about attacker nodes, which are the nodes to which attacker has access, and attacker can modify these nodes. Okay? That's the idea. Now, what can an attacker modify? We can talk about a direct attack where the attacker node is also the target node. And the attacker can modify the target node by changing its features, right? And it can also change who the target node is connected to, okay? Which means it can add connections or it can remove connections, right? It could cut a link, it could add a link, or it could change the features of the target node. So that's one attack possibility. And we call this a direct attack because we are attacking directly the node of interest. There is also a more sneaky indirect attack, right? In an indirect attack, the target node is different from the nodes that attackers are attacking, right? So what can the attacker do? Basically, for these attacker nodes here in blue, the attacker can change their features, the attacker can add connections, or the attacker can break connections. Like similar, but now to the nodes that are not the one for which we care to flip its label, okay? So what's the objective function of the attacker? The attacker wants to maximize the change of the target node's label, change the prediction, subject to small graph manipulation, okay? So the intuition being, if graph manipulation is too large, maybe we will be easily detected. So the successful attacks should change the target prediction with kind of unnoticeably small graph manipulation, right? So the idea is, I want to flip the label of this node. Maybe I do, maybe I add an edge, maybe I flip some attribute, and all of a sudden I get a completely different prediction, right? So after the attack, maybe I want the probability of class 3 to increase, but probability of class 2 to decrease, or something like that. That could be my goal. So the way you can formalize this is the following. Let A be the adjacency matrix of the original graph, and X be the feature matrix, the features of the nodes. And after the attack, we are going to have a different adjacency matrix, A prime, and a different feature matrix, X prime. And what we would like to do, what the attacker wants to do, is to make this perturbation, this attack, as small as possible. So we want graph manipulation to be small. And here, again, graph manipulation could either be direct, changing the connections of the target node, or we can be in indirect attack, where the attacker is attacking non-target node. So that's the first thing to say. So the way we are going to formalize this is the following. We are going to say we have the original adjacency matrix, original features, and node labels Y. We are going to have some model parameters learned over A, X, and Y, so over graph, features, and the labels. Let's C be the class label of node V predicted by the GCN with those parameters. Now we assume that the attacker has access to the graph, features, and the labels, as well as the learning algorithm. And what the attacker can modify, the graph, and the attacker can modify the features. now if the attacker makes this modification, we would unknowingly learn a different model, a model theta star prime, that is now learned on the attacked graph, attacked features, but with still the original labels, right? And now I'm going to use this C star prime to denote the class label of a node V under this different model. And the goal of the attacker is to flip the label of that node V, right? That the labeling when training on the clean data is different than the labeling when trained on the attacked data, okay? So the mathematical formulation goes as follows, is that for the target node V, I want to learn the GCN over the original graph, and I'm going to use this C star to be the predicted class of the GCN that was learned on the original unattacked data. Then the attacker comes and manipulates my training data. So I'm going to, so what will happen in that case is that now the network that I'm going to learn, the neural network parameters are going to be different. I will learn this theta star prime. And also because now parameters are different, the label, the predicted label for that node V might be different. And the attacker, what they want to do is they want to change the prediction after the graph is manipulated from one class to a different class. Okay, that's the goal. So how do we formalize this? Right, the way we formalize this is we want to identify the amount of likelihood or the confidence the model has in one versus the other label. Right, we want the probability of the log probability of the newly predicted class. We want to increase this term, but we want the predicted log probability of the originally predicted class, we want this to be low, so that it's going to flip. This is going to be larger than that, so we are going to conclude wrongly under the new network that this is the correct class for the node. So the way you can now write out the optimization problem that the attacker is trying to solve, the attacker is basically saying, I'm trying to change this delta, I'm trying to push this probability up, or this log likelihood up, and I want to push this log likelihood down, right? I want this to be small, and I want this to be large. I want to do this by manipulating A and X to get the A prime and X prime. The solving this optimization problem, if you are an attacker, is very hard. The reason is that because adjacency matrix is a discrete object, so you cannot take derivatives. And then whenever you make a manipulation, you need to retrain your graph neural network to see how it changes its predictions. So you have both kind of the optimization problem as well as kind of the scalability problem. The paper that was published at KDD 2018 was the first one to kind of formalize this framework, which I gave you the formalization. And they also provided a lot of clever techniques to kind of resolve these two problems. And basically what they come up is this kind of locally optimal strategy where they, in a greedy way, try to execute a series of perturbations and sequentially manipulate the graph, basically sequentially manipulate the most promising element to try to flip the label. And the way they do this is they have this delta objective function, this difference in log likelihoods, and then they basically, which indicates the score, and then they pick the perturbation that maximizes the score. And they keep picking the greedily best perturbation until the label changes. Okay, so that's what they do. Yes?
Why in the setup do we assume the attacker can only change the adjacency matrix? Why not also the labels for training?
Good question. So the question is, why are we assuming the attacker cannot change the labels? If the attacker could change the label, then it's easy. I just change your label and you'll be classified differently tomorrow. So that's a very easy attack. So now, of course, maybe what we should do, maybe if I answer a bit more seriously, right, is like, I think, there are different attack scenarios, right? Here they said, I allow myself to retrain the network. I think a completely reasonable attack scenario would be that you have your A, X, and Y, you train your model, but now A and X can evolve, they can change, but the model remains fixed. How should I change that to flip your label? That would be another different scenario, right? It would be like you trained the fraud detection system. Now the question is, how do I organize my financial transactions that go through your fraud system, right? So I would say different formalizations make sense. Here the authors pick the one where they say you don't have access to labels because labels are external. I think my sense is that if you have access to labels, then it's much easier. It's kind of easy, right? So that's maybe the reason why they choose this one. That's a bit more challenging.
In order for the attack to succeed, does the attacker need to know the structure of the model itself?
Correct. In this case, we are assuming the attacker knows the structure of the model itself. In all these adversarial examples, you need to have access to the model. Yeah.
Has anyone tried to use a deep reinforcement learning to train the attacker because it appeared that?
Good question. So you're saying, has anyone used the reinforcement learning to train the attacker? So you could say, I have a model that's a black box, but it would take you, but in most cases, especially in the computer vision, they assume you have actually access to the parameters. I think in this case, I would need to check the paper, but I think they don't really look into the parameters of the model, but they assume they know what model you are training. So at least they have to have. Could you do reinforcement learning? You may to learn the attack strategy. I think it would take, training would be super hard and it would take super long.
So is this kind of similar to map estimation or detection ideas? Like you rotate through every single hypothesis, compare it, and then choose the one that returns the maximum likelihood?
Sure, this is just a greedy algorithm. It's just you, like, rather than trying to find the optimal, which you can't, you execute the search step by step, and at every step you just do the best thing that is best in that given moment, even though it might not be globally optimal. Okay, good. So I want to show you some results, just kind of as a discussion because I thought was interesting. So this setting is semi-supervised node classification with a graph convolutional neural network. Graph is a small citation network, 2,800 nodes, 8,000 edges. The attack type is modify edges, add or delete them. And the attack budget is that you can change the degree of the node for 2. So you can either add up to 2 edges or delete up to 2 edges. And the intuition is that it's harder to attack a node with a larger degree. And the model is trained and attacked 5 times using different random seeds. So you kind of see also success rate. So here is, these are now predicted probabilities of the target node over 5 different learnings, right? So this is now, this is a 7-way classification data set. This is the predicted probability for that given target node to belong to a given class. You see we are correctly predicting this node to be in class 6, which is good. The reason why each bar here is a different experiment. So, it's a different training run from a different random starting point, and because of this there is some variance in what your model converges to, but the point is in all cases the prediction is correct. Okay, so what we want to do now is we want to change the underlying graph to make this node belong to class number 7. You know, whatever that number 7 is. Okay? So let's look how whether the model was able to do this. So here, after modifying just 5 edges in the underlying network, this was with a direct adversarial attack. You can see it completely changes. Right? So here we modify 5 edges of the target node with a targeted attack, and we were able to convince the neural network that the node now is of class 7. If you look at kind of more broadly the results in this paper, basically they find that the adversarial attack is the strongest attack, significantly worsening the GNN's performance compared to the no attack. They find that randomly attacking, randomly adding noise is much, much weaker than adversarially attacking the network, and that indirect attack is more challenging than the direct attack. And here I can interpret the results with you. Here is the classification margin. If it's negative, the attacker succeeded, and it was a misclassification. And basically, what you see is that with a direct adversarial attack, you can basically always flip the node's label completely, right? What they find out that if you add random attack, this is random edges between target nodes and nodes with different labels, random doesn't even work. Even though you can do a random targeted attack, so you can attack the target, random manipulation doesn't do much. Sometimes it flips, but most often it doesn't. So in this respect, GNNs are quite robust to random noise, either on the target node or on the nearby nodes. And here is the adversarial indirect attack, and you see that this is not really successful, right? That indirect manipulation is much, much harder. And of course, it remains, I think, an open question. What could you do with adversarial indirect attacks, and how would you be able to manipulate the network in the vicinity of the target node to flip the target? That could be quite cool if you could master that. Okay, so let me just summarize what we studied in this last part of the lecture today. We studied the adversarial robustness of graph convolutional neural networks applied to semi-supervised node classification. I showed you, basically we formalized the problem, talked about direct and indirect attacks, both on the graph structure as well as the node attributes. And I showed you kind of some experiments that are suggesting that targeted attacks are easy and effective, random targeted attacks are not effective, and doing indirect attacks is very hard. So in some sense, if somebody wants to manipulate the target, they can easily do that. Other types of manipulation seems to be much harder to pull off, which is very encouraging. And also, I think what is encouraging is that this random noise, GNNs seem to be quite robust to it. So with this, I'm done for today.